So welcome everybody. Today we are very happy to have Wilbur to end our Friday seminar series for the semester. And he will tell us about anomaly detection in 2+1d Lattice.
Thanks, Ahan. Thank you for the chemistry. So before I start, let me just acknowledge my collaborators. This talk is based on two parallel projects. The first is with Michael Levin at Chicago and Kyle Calico, who's a postdoc at Ohio State University. And the second project is with Kyle and Sean Sanford, who's also at OSU. Okay, so let me begin with a very brief general introduction. So a global symmetry of a quantum system is said to have a Hooft anomaly if there is some obstruction to consistently gauging the symmetry. So this kind of anomaly is very useful for constraining the dynamics of the system. And in particular, a system with some anomalous symmetry basically is not allowed to lie in a trivially gapped phase. Either it has to be gapless, or if it's gapped, then there must be some either non-trivial topological order or some form of spontaneous symmetry. So on the other hand, Hooft anomalies are particularly useful for characterizing SPT phases in one higher dimension. So in particular, a system with an on-site, or in other words, an anomaly-free symmetry, lies in a non-trivial SPT phase if and only if the symmetry acts in an anomalous way on the boundary of the system. This is the so-called bulk boundary correspondence for SPT phases. So in this talk, I will be talking about basically the most basic kind of symmetry, which is just an ordinary zero-form global symmetry. And in particular, I will focus on internal rather than space-time symmetries. And I will always be talking about some finite group symmetry. So it's generally believed that SPTs are at least partially classified by the group cohomology of the symmetry group with U1 coefficients, where the degree of the cohomology corresponds to the space-time dimension. Okay, so there's sort of some standard methodology for detecting anomalies, especially in a continuum. So the basic idea is that we couple the system to some background gauge fields and then check to see if the partition function is gauge invariant. If it's not, then that indicates the presence of an anomaly. But for generic internal symmetries on the lattice, this sort of methodology is not really applicable, basically because there's not a clear notion of what it means to couple to background gauge fields. So basically for lattice systems, we need some alternative method of diagnosing anomalies. So this problem has been well studied in the case of 1+1 dimensional systems. And there are a couple well-known methods for diagnosing anomalies in 1+1d. So in particular, there's a method which basically examines the structure of symmetry defects in the system. It was sort of first discussed by Levin and Calgo, and also generalized more recently in a very nice paper by Sahan to the case of lattice translation symmetries in addition to some internal symmetry. There's also a method developed in a very nice paper by Elsa Nyack, which is basically uses the idea of symmetry restriction to diagnose the anomaly. So basically the goal of this talk is to provide methods in 2+1d for similarly diagnosing Hooft anomalies in lattice systems. And so basically what I mean by this is if you give me some 2+1d G-symmetric theory as the input, then the output of the method should be a cohomology class belonging to cohomology group H4 G with U1 coefficients. So in particular, what do I mean when I say a G-symmetric theory? Well, I'm sort of using this in kind of the minimal sense of the word theory. So by a G-symmetric theory, I just mean basically 3 pieces of data. So for one, there's some Hilbert space. And secondly, this Hilbert space needs to be equipped with some notion of locality. And that's basically achieved by giving some complete list of all the local operators on Hilbert space H. And of course, we also need to say what we mean by our G symmetries. And so for every group element, we'll have some locality preserving unitary operator U sub. So by locality preserving, I just mean that unitary UG maps local operators to local operators, and moreover, some local operator is supported in the vicinity of a particular point, then the image of that operator likewise has to be supported in the vicinity of that same point. We were talking about internal, not space-time symmetries. So this is the goal. And I'm going to describe 2 distinct methods of accomplishing this goal.
Sorry, when you say vicinity of the point, do you mean at the point in the lattice, or do you mean that you also allow the change in like adjacent points around the lattice?
It could act on adjacent points, just in the vicinity just means some small region around them. Right, so I will actually give 2 different methods for diagnosing anomalies of this kind. So sort of a key point that I'd like to stress is that a Hooft anomaly is really a kinematical property of theory. And that means that it's a property of the Hilbert space and the symmetry operators alone, and it's sort of independent of the dynamics of the system. Right? That being said, introducing dynamics into the system can be a very useful probe of the anomaly. So while it's not essential to have dynamics, it can be useful to talk about some particular Hamiltonian. So the first method is precisely does this. It's sort of called the dynamical approach. The idea is that we sort of get to choose any Hamiltonian that we want that respects the symmetries. And so we might as well choose a Hamiltonian that is particularly convenient for analyzing the anomaly. So in particular, we'll choose gapped Hamiltonian that spontaneously breaks the symmetry. And the anomaly will subsequently be encoded in the algebraic structure of the ensuing domain walls. The second approach that I'll discuss is what I call kinematical approach. And the basic idea is that an anomaly is an obstruction to truncating the symmetry to some finite region while preserving the group multiplication level. So I'll sort of make this idea a little more precise. This is very closely related to the idea that anomalous symmetries end at the boundary. And let me mention that these 2 methods are basically suitable generalizations of the existing methods in 1+1d. Okay, so let me just briefly outline the remainder of the talk. So for both of these approaches, I will basically review how it works in 1+1d, and then describe how each method can be generalized to the 2+1d case. And then I will compare the 2 approaches. So if we have 2 methods of calculating the same thing, they better give the same answer. We'll see that they do indeed give the same answer. Okay, any questions at this point? Okay, good. Okay, so I'll start with what we call the dynamical approach. And me start with just a basic outline of the procedure. So like I said, the first step is to choose a particular Hamiltonian H. And we want our Hamiltonian to have the following properties. So obviously it has to be local. It has to be just a sum of some local operators. Second, we want it to be gapped. Third, we want it to be short range entangled. So there's no anion excitations. There's no intrinsic topological order. And lastly, obviously Hamiltonian should be symmetric, but we want a Hamiltonian that spontaneously and completely breaks the symmetry. So because the symmetry is completely broken spontaneously, there will be order G generic ground states, which we are free to label by elements of the group G itself. And the sort of elementary excitations of the Hamiltonian will be domain walls that interpolate between two distinct ground states. And as I mentioned, the basic idea is that the anomaly is encoded in the fusion rules of these domain wall excitations. So what exactly I mean by fusion rules is sort of dependent on the dimension that we're working in. So
You can always choose such a Hamiltonian.
yeah, so at the beginning I stated that G, I will take G to be a finite group symmetry. And so I think it's generally believed that such a Hamiltonian can also be chosen. Certainly don't know of any counterexamples. Okay, so as I said, let me sort of start with the 1+1 dimensional case. So the basic idea in 1+1d is that so domain walls are point-like objects in 1+1d, and they can fuse with one another, and they have F symbols, which sort of describes the associativity of fusion. So sort of basic sort of schematic idea is that we start with some state which has a single domain wall of type GHK, and we sort of start with this state, and we enact some process that will give us two different states, 1 and 2. So the first state 1 is obtained by first splitting the domain walls, the original domain wall into a GH domain wall and a K domain wall, and then splitting the GH domain wall into a G and an H domain wall. And the second state, state 2, is obtained by first splitting G off from HK and then splitting HK into H and K. So in these diagrams, this is like a space-time process where the horizontal direction is the spatial axis and the vertical direction is the time direction. And the basic idea is that the domain wall F symbol is the phase difference between these two states. Okay, so
Could you remind us why the domain wall is labeled by group element?
because different ground states, there are G different ground states. So the domain wall between two different ground states naturally associate the group element. So if we have a ground state labeled by G and a ground state labeled by H, then the domain wall between those two ground states will be labeled by GH inverse.
So the label of the first vacuum doesn't matter? If you have one ground state, in principle, there might be two labels, right?
Yes, that is
always
correct.
the left boundary condition to be in some ground states.
Yeah, so I'll go into a little more detail in a second, but basically the procedure that I'll describe sort of independent of which of these states. So basically it doesn't matter what the ground state is to the far left. And so why does the F symbol defined in this way? Basically, why is it a free cocycle? Basically, the F symbol obeys a well-known constraint known as the pentagon equation. And Basically, in this context, the pentagon equation is derived in the following way. So we basically imagine 5 inequivalent space-time processes, all of which start with a state that has a single GHKL domain wall, and then basically this single domain wall is split into 4 different domain walls via 5 inequivalent space-time processes. And so this basically defines 5 different states, 1, 2, 3, 4, 5, which are all the same up to a phase. Basically the way we derive the pentagon equation is by sort of comparing the phase difference between state 1 and state 5 in 2 different ways. So on one hand, we can compare the difference between 1 and 2, and then 2 to 5. On the other hand, we can compare the phase difference between 1 and 3, then 3 to 4, and then 4 to 5. These 2 phase differences are the same, and therefore we obtain the pentagon equation, which is simply the 3 cocycle condition on F. And so as a result, we find that F is a 3 cocycle. Moreover, we find that there's an ambiguity in the F symbol, which precisely corresponds to the coboundary transformation. And the way to see this is to note that basically these 2 independent spacetime processes that define the F symbol they basically involve 4 splitting operators, which I've sort of called S. And
So all these states are bound states?
these are states that have some finite number of domain wall excitations.
Oh, I see. And F symbol describes how like 2 different states translate into each other.
Yeah, it basically describes the phase difference between 2 states which are constructed with 2 different processes. And so the idea is that we have these 4 splitting operators, but sort of the phase of the splitting operator is sort of ambiguous. And so if we redefine the splitting operators by multiplying by some phase, which depends on the 2 group elements G and H, then we find that F transforms by this coboundary. And therefore F is not just a cocycle, but it defines a cohomology class. Okay, so
the space-time process, are you actually thinking of just implementing a unitary step-by-step that actually that just moves the domain walls physically?
Yeah. So actually, what I've described is sort of a schematic picture, but yeah. So now what I want to do is sort of give a more precise operational microscopic definition of.
Let me just ask another remedial question. What's the smallest group that has such a cocycle?
Z2.
Okay.
H3 of Z2 with Ewing coefficients is Z2.
Okay.
1 non-trivial Z2 anomaly and 1 right. So basically, to answer your question, so what this F symbol is measuring. So this F symbol is a phase difference between 2 states, but alternatively, it can sort of be thought of as a Berry phase accumulated over the course of some spacetime process. So if we sort of take state 2 and flip it upside down and then compose it with state 1, this would sort of represent some process that comes back to itself, and then there's some Berry phase. But sort of there's a subtlety here, which is that this Berry phase, if one is not sufficiently careful, then the F symbol one gets basically will have some non-universal contributions to Berry phase, sort of renders it physically meaningless. And so sort of to get something meaningful, we have to be very careful about exactly what we do. And so I will describe some very careful procedure which sort of isolates the universal contribution.
It issues that I can assign several distinct stories to your slides, but somehow you use all three of them simultaneously. That's why I'm puzzled. Number one, talk about Berry phase. Berry phase, you change parameters in the Hamiltonian, track a state. Number two, to describe is a time-dependent process in the same Hamiltonian. You don't change the parameters, but there are some states with domain walls. Number three, use the same Hamiltonian. There's no domain wall, but you get the trivialization of the background gauge field. So whatever you said fits the three different stories. Somehow you didn't commit to one of them or the other. Or more I should say, kind of describe the three of them simultaneously and not distinguishing between them.
Okay, so
Is this a time-dependent process given Hamiltonian, or is it a multi-parameter Hamiltonian where you vary many parameters and you track a state, or is it just changing the trivialization of the background gauge bundle?
So if you want to interpret this phase as a Berry phase, then we would sort of have some Hamiltonian which is very slowly varying in time, and for which sort of the state, sorry, and for which the state at some fixed time is sort of the ground state of that Hamiltonian. So that's sort of how we interpret.
So which of the three stories are you going to follow?
The second. So in sort of precise microscopic definition that I'm going to discuss now, it's basically it'll be the second. Yes. Okay, so as I mentioned, we would like to have some procedure that sort of isolates the universal part of this Berry phase in order to have something which really truly diagnoses the anomaly. So let me describe basically how to turn that schematic picture that I just described into sort of precise operational definition of the F symbol. Okay, so the first step is we just choose some mesoscopic lattice of points, x1, x2, all the way to xn. And basically these will be points where our domain walls reside. Second, we want to basically fix once and for all a sort of canonical set of domain wall states. So these domain wall states will sort of be required to satisfy certain properties. So first of all, every domain wall state away from these points x1, x2, etc., should look like one of the degenerate ground states, right? Then for each point, we basically we associate a group element to each point x1, x2, etc. So we have G1. So this is just saying that sort of group element G is associated to point 1, and so on and so forth. And so basically, the domain wall state is characterized by these group elements, and also there's this group element M, which basically describes the domain to the far left of all domain walls. So we have a domain wall state for every assignment of group elements to sort of these points, but also we need to specify what the ground state is to the far left. And so we fix these domain wall states, but we sort of have some additional requirements on the domain wall states. They're not totally arbitrary. So first of all, if the states are the same except for the label here, then we require that these two states are symmetry partners. And secondly, we require that if two domain wall states have the same kind of domain wall at a particular point xj, then these two states should look the same in the vicinity of that point up to a symmetry transformation. Okay. So we fix the set of domain wall states. Then we also want to fix a set of splitting operators, which we will require to be symmetric under the symmetry. So each splitting operator is associated with a pair of group elements as well as an index J. And the basic idea is that Sj of G and H will take a state that has a domain wall type GH at point xj, and it will map it to a domain wall state where there's now a G-type domain wall at point J and an H-type domain wall at point J plus 1. So this is sort of how the splitting operators are defined, and we sort of just choose some arbitrary set of splitting operators that satisfy these properties.
All right, this is a dumb question. What do you precisely mean by symmetry partners?
I just mean that there's some symmetry that takes one state to the other. Some symmetry operator.
Non-local.
Well, it'll act on the entire system.
Related to my previous question, are these exact eigenstates of the Hamiltonian or not?
Not necessarily. Just some.
There's no Hamiltonian.
Well, there was a Hamiltonian that created these ground field.
We do have a Hamiltonian, but yeah, we don't require the domain wall states to be eigenstates.
There's a big Hamiltonian that has some number of ground states. And there are excitations that depend the details of the Hamiltonian, which are the labels of ground states. Now, every one of them could be deformed a little bit, especially because they're not eigenstates. So for example, if I have a domain wall here and the anti-domain wall here, there's some attraction between them to minimize the energy. So you need more assumptions here, how you treat subtleties.
So there are many sets of domain wall states that we could choose. There's no canonical set, but we just want to pick a set for every possible domain wall configuration, and we sort of require that the set is sort of self-consistent in these two ways. But other than that, the set of domain wall states that we pick can be arbitrary, but we're going to fix them once and for all at the outset.
Are you assuming that the distance between the points is much bigger than the energy gap?
That's basically what I mean by mesoscopic.
States are independent of the distances as long as they're bigger than some multiple of the last space figures. But
Yeah.
Anomaly is SJ as unitary or not?
SJ does not have to be unitary. And
What's the property of it?
okay, the property is that it's symmetric. And it
When we symmetric,
meets with the symmetry operators.
that's it, okay. And it doesn't have, but it has to be local.
It has to be local, so it basically has to act in the region between J and J plus 1.
And you don't have a weaker condition that replaces unitarity, so S is not unitary and no condition.
No, it just has to act in the correct way on domain wall states.
All of them.
Yeah, so okay, so first of all, this the proportionality constant is just phase, but basically
But wait, sorry, if it's not unitary, why is guaranteed to be a base? Can be any number, right?
yeah, but that's something we want to impose on it. Okay, yeah, that's a requirement. And basically, so we actually only need this to be true for some domain wall state, which is the particular one I've written here. And basically these properties guarantee that S will have the action that we expect on all the domain wall states. Basically because of these properties and because of symmetry of the splitting operators.
Okay, my question, we can think of these G labels as boundary conditions at W. for two
boundary
conditions. Yeah, like so let's analyze right there are two Hamiltonian spaces and boundary conditions there. Specifying what is.
there's only one Hamiltonian, and there's sort of degenerate ground states. So domain wall state is one that, so if there's a single domain wall, that means that we have one particular ground state to the left and one particular ground state to the right, and some excitation in between.
I think that what he said is also correct. That's why there are several different descriptions of the same thing. You can do the whole thing without ever mentioning the Hamiltonian. You just say that there are boundary conditions at that point. And then usually the name associated with it is a defect. So whenever you say domain wall, if you say the defect, then what he said would be correct. In fact, that would also make it obvious it's independent of the details of the Hamiltonian.
Yeah, you could sort of bring things in a more general way, but I think this is kind of the simplest thing you can do.
Actually, if it's if I think of it as a defect and it's not giving you eigenstate, why is it labeled by group G? Can I get some very random boundary conditions?
We have well, in the case of a spontaneous symmetry breaking Hamiltonian, there's some degenerate ground state to the left and some ground state to the right, and so each of these ground states is labeled by some group element, and so therefore that fixes the label of domain wall.
I think he's right. This is a choice.
Yeah.
Because
It's an arbitrary choice. It's an arbitrary choice of which domain wall state is chosen. It could be any state in that sector.
when you pick the general ground states, you pick the basis. Basis that diagonalize the local operators. Once you pick a basis, every one of these is a transformation between them. For that, you need to choose a basis. For example, if you have n state, you could pick a state which is invariant under the group. That would be S state among the degenerate states if they are exactly degenerate. And then in every region, you could put the invariant state. There's a choice of basis that you make.
Well, yeah, we don't want like cat states. Is that what you're saying? So we could have some cat state. Cat state. Schrodinger's.
You have n states. So imagine the symmetry is Z2. So you have two states. You can think of them as being the symmetric, the asymmetric one. That is not going to work, what you say. Alternatively, you can think of them as being plus or minus. That's a different basis. I think you have in mind the second basis, yes, rather than the first one.
Yes.
So it involves a choice of basis. And that's related to the question he just asked.
You have the condition that these are short-range entangled states. I think that
rules out
equivalent to
these cat states. That's developed, but yeah, but those are ruled out. Thanks. Okay, so we choose a Hamiltonian, we choose a set of dimensional states, and we choose a set of splitting operators. So how do we extract the anomaly cocycle? Well, we can sort of do the same thing that I described earlier, where we start. So we start with a state that has a GHK domain wall at point x1, and then from there we define two states, 1 and 2, using the splitting operators that we've defined. So on the left we have this first splitting operator and second splitting operator both acting at point 1, but on the right hand side we now have a splitting operator. The first splitting operator is at point 1, but the second splitting operator is at point 2. And we define what I'll call bare F symbol F naught, which is the phase difference between states 1 and 2. But sort of the issue that arises is that we've used sort of two different sets of splitting operators to define F naught, because we have S1 and S2 operators. And each of these operators, or each set of operators, has an independent phase ambiguity. So in particular, we can multiply S1 by some phase alpha 1. We can also multiply S2 by some phase alpha 2. All of these sort of functions of pair group elements. Okay? And the issue is that when we redefine splitting operators by multiplying them by phase, then this bare F symbol, F naught, changes by a quantity which is not a coboundary. Because it has this alpha 2 here and alpha 1 in these three spots. And so basically what that's saying is that F naught, the bare F symbol, does not correspond to some cohomology class. And so it's not the F symbol that we're after. So basically, how do we get the true F symbol out of F naught? And basically the solution is to use a very nice trick, which as far as I know was invented by Sahand. And the idea is to define the F symbol, the true F symbol, as a ratio of these bare F naught symbols. So in particular, the ratio has as the numerator the F naught of GHK, but in the denominator we have F naught of 1HK. And the idea is that whereas F naught transforms by more than a coboundary when the splitting operators are redefined by multiplying by phase, this true F symbol, which is the ratio of two F naught symbols, changes by a coboundary. In particular, it's the coboundary of this function alpha, which is itself a ratio of two phases, two alpha 1 phases.
But why can't you just choose all this J's to be equal, I mean, since that it's just a local property?
If you're asking why can't we just sort of choose all the splitting operators to occur at the same point?
Well, not at the same point, just to be the same, depending on the local properties. I mean, why does it matter which say it happens on?
I guess you could only do that if you have translation symmetry, but
Right.
here,
Yeah, okay.
I think it's.
Okay, so we don't assume any
Yeah.
translation. Yeah. But in the absence of translation symmetry, this prescription gives us a method for computing the true F symbol. And so clearly F has coboundary ambiguity. It can also be shown that F is a cocycle, and therefore F defined in this way is genuinely an element of the cohomology group H3. Okay. So this is the story in 1+1 dimension. Now we want to generalize to 2+1. Okay, so in 2+1d, domain walls are now one-dimensional objects, and the main subtlety, or sort of the novelty of domain walls in 2 dimensions, is that they can branch. So in particular, if we have a G domain wall and an H domain wall, they can come together in space and fuse to a GH domain wall. Okay, so let me just point out that sort of from here on out, whereas previously we had sort of space-time diagrams, now both the vertical and horizontal axes are spatial directions. And so this picture is a picture of a spatial domain wall configuration. Okay, so the question is, what is sort of the analog of the F symbol in one higher dimension? And the answer is that the analog of the F symbol is something that's called a 10J symbol. So basically, if in 1+1d, the F symbol measures the failure of domain fusion to associate, then analogous statement in 2+1d is that the 10J symbol measures the failure of domain wall associativity to pentagonate. And so for that reason, the 10J symbol is also called a pentagonator, sort of in analogy with associator. Okay, but this probably isn't a very helpful thing to say, so let me explain what's going on here. So Right, so as I said, basically each of these diagrams represents a spatial configuration of domain walls. And we sort of do an analogous thing as we did in 1D. So we start with a particular domain wall state, which we'll call state 0, and then we define two states 1 and 2, which are identical up to a phase. And basically these states 1 and 2 are obtained from the state 0 via two distinct space-time processes. So on one hand, so there's this process in red where we start with state 0, sort of form the domain walls in this way. So if we start with the state and then move the K domain wall here, and then we move the H domain wall there. And so thus obtain state 1. And we sort of do a similar thing along the bottom of the pentagon to obtain the state 2. Then the 4 cocycle omega is defined as the phase difference between these two states.
So why do you have to consider fusion of 4 domain walls here? Why not 3?
Well, so sort of the very short answer is that we need something that's a function of 4 group elements to define a 4 cocycle. And yeah, basically this is how it's done, is looking at these two distinct processes. So
How are the domain walls oriented? Before it was line, these were points.
oh, well, so in all of the diagrams that I'll draw here, basically the arrows always point up.
So is that a process in 1 dimension? Is this a process in 2 dimensions?
So remember that this is a spatial configuration of domain walls, and generically there should be orientations on these lines, and I just haven't drawn them.
It's not just orientation, these are domain walls in the XY plane. They could be arranged in a complicated configuration.
Yes.
Now you start moving them. Does it depend on how they are arranged or not? Because you don't have this extra information here.
Sure.
When you have points on a line, they just take snapshots and space is a line, and you have points where you have the domain. Function of time, these points move. Now, these are lines in the plane. That's the lines in the plane. Each of them labeled by a group element. Now you start moving them. You start fusing them. Does it depend how they are oriented or not? Or do you assume that they're all parallel?
So in your picture, each of these are snapshot, and the red arrow, for example, is a time, right? So
Yes.
that would be the second snapshot, and there is one interpolation between them.
Yeah.
But the detail how you interpret, how you implement this time direction doesn't matter. Is that?
Well, technically, that's about the angle, it's viewed within at 45-degree angles, but because only they can figure on the top, they can't really both be at 45-degree angles, because then they would intersect, so right, you need this curve then and so on. I mean, so the question is, does it depend on all these angles? Things or can you prove that it's independent of that?
So again, this is sort of a schematic picture. Momentarily, I'll sort of give a more precise microscopic definition, and that hopefully should clarify. Right, so okay, but first I want to explain why the omega defined in this way satisfies the 4 cocycle condition. And the basic idea is to look at the associahedron. So the associahedron is basically the generalization of a pentagon up 1 dimension. In fact, the pentagon itself is an associahedron in 2 dimensions. And okay, so basic idea is that every vertex of the associahedron now corresponds to a spatial domain wall configuration. And so all of the edges of the associahedron are oriented, and there's sort of 2 sort of special vertices of the associahedron. The first one is this point here, for which all the arrows are outgoing. And the second special point is this point here, for which all of the arrows are ingoing. Now, each path from this vertex to this vertex, for example, we have this path here, corresponds to some space-time process in which we start with one domain one configuration and end the other domain one configuration. Basic idea is to consider two distinct paths. So on one hand, we can consider this path here, and on the other hand, we can consider, say, this path here. And we basically want to compare the phase difference between these two paths in two different ways. Basically, one way is to sort of go around one hemisphere of the association. The other way is to go around the other hemisphere of the association. And in doing so, we obtain the four cocycle condition on omega. Basically, the way to see that is that there's 6 pentagonal faces of the association, and each one of them corresponds to one of the factors in the four.
What is C4?
C4 just means a set of 4 cocycles. So omega is a cocycle. Likewise, there's also an ambiguity in the definition of omega. So basically, the definition as a phase difference between these two states sort of depends on we sort of use 5 different F-move operators in the definition of these two states. And if we basically redefine these F-move operators by multiplying them by some phase alpha, then we see that omega transforms precisely by a 4 cobordary. Therefore, omega defined in this way sort of gives us an element of the cohomology H4. Okay, so basically, what I said in the 1D case about sort of accumulation of potentially non-universal phases also is an issue in the 2+1d case. And so it requires some sort of microscopic definition of the cocycle, which sort of properly isolates the universal contribution to this phase. And so how do we go about doing that? Sort of an analogous procedure. So we start by fixing some mesoscopic honeycomb lattice in our 2 space dimensions. And we also fixed some domain wall states for every possible domain wall configuration, which we'll call it. So eta is just some configuration of domain walls. In this case, the domain walls live on the edges of our mesoscopic honeycomb lattice. In addition to the domain wall configuration eta, we also have to specify a group element M, which basically is just the label of the ground state far to the left of all domain walls, sort of in analogy to the 1+1-dimensional case. We also have sort of place similar requirements on the choice of domain wall states. So in particular, if 2 domain wall states have the same domain wall configuration, but a different group element, then they must be symmetry partners. Moreover, we require that any two domain wall states that sort of have the same domain wall configuration within some particular region, basically these 2 states must look the same within that region up to a symmetry transformation. And that's sort of an analogous requirement to the one that we had in 1+1 case. So we define domain wall states with these requirements in mind. And then secondly, we sort of now need the analog of splitting operators that we used in the 1+1d case. And so now basically we have a set of, we need to define a set of F-move operators. And we likewise require that the F-move operators are symmetric. They're sort of locally supported, and they map domain wall states to domain wall states sort of in the way that we expect. So in particular, we have an F-move operator associated to each plaquette of the honeycomb lattice, which transforms domain wall state that looks like this to a domain wall state that looks like this. And for technical reasons, we also need to define two Plaquette F move operators. So these are sort of same idea as the single Plaquette F move operator, but now they sort of enact an F move across two Plaquettes. Right, so we have this sort of Q type F move and this QR type F move.
You cannot construct it from above.
You could if you wanted to. It turns out that I think this is a slightly cleaner way of doing things.
So even though they might be dependent on each other, but we don't care.
We don't care. Yeah, they could be in principle independent. Yeah, basically the form of the two Plaquette F move operators is not fixed by our choice of single Plaquette F move operators. Okay, so we've chosen the Hamiltonian, we've chosen a set of domain wall states, and we've chosen a set of F move operators. So now how do we define the anomaly cocycle? Well,
It's related to the question I asked them. You have all these phases in F and all that. To what extent does it depend on the microscopic Hamiltonian?
So the domain wall states will depend on the Hamiltonian because they have to look like ground states away from the domain walls. That's basically the extent of.
But when you start fusing them, does it depend on details or because the profile of the domain wall to have some field that moves depends on the terms in the Hamiltonian. For example, width might depend on the details of the height.
Yeah, but
And when you start fusing them, you have to make sure. I'm asking to what extent this depends on all these microscopic details. The reason I ask is that I said that there are several different perspectives of the same pictures. From the other perspectives, it's clear that it's independent. It depends only through this cohomology class, but does not depend on, other than that, on all of the details of the Hamiltonian. So for example, in the Hamiltonian, you can put some next to nearest neighbor interaction.
so the domain wall states depend on the Hamiltonian only insofar as the requirement that they look like ground states away from the domain walls. But they're sort of the form of the domain wall states in the vicinity of the domain wall is a choice that we make. It's arbitrary. So the domain walls themselves don't really have any dependence on the Hamiltonian.
Okay, but now you start fusing them. You get different phases by fusing them in a different order.
We fuse them with operators which are chosen to satisfy some requirements, but none of those requirements sort of depend on the form of the Hamiltonian. We sort of require that the F move operators map domain wall states to domain wall states.
So why do you need the Hamiltonian in the first place? You said that the way I hear you, almost nothing depends on the Hamiltonian.
Well, in principle, we don't, because the anomaly is not a property of the Hamiltonian. But a choice of Hamiltonian, it's just sort of a convenient way to package it all together.
Different microscopic Hamiltonians give you different representatives of the cohomology class.
Yeah.
So you'll get different actual values of the Fs.
You will, and
But they're different by a cohomology
Yeah.
boundary operation.
yeah, and different choices of domain wall states and F move operators also will give you different.
No, it could just be a phase would be various phase redefinitions of the states.
That's not the same as co-boundary.
Yeah, yeah.
operation.
Because the co-boundary just relabeling the states by some phases. It doesn't depend on the Hamiltonian. If you take the Hamiltonian, it has some parameters, if the knobs are changing, none of that story will change. You can arrange the phases, co-energies, in such a way that it's completely independent of the type. This is a standard picture of the renormalization. There's a story in the IR, which is independent of all the details in the UV.
Well, to answer your original question, yes, these choices will affect the precise representative of the cohomology class, but they will not change the cohomology class itself. Okay, so to proceed, what we do is we sort of define this bare omega symbol, omega naught, in sort of an analogous way. So we start with this state 0, which has this particular domain wall configuration, and then we define two states, 1 and 2, which are the same up to a phase. And we define these states using our F-move operators. So see this bottom path, we use 3 separate single plaquette F-moves. We want to support our plaquette P, plaquette Q, and plaquette R. Whereas for this top path, we need to make use of these 2 plaquette F-move operators that we defined. And so we get some phase omega naught. But once again, we've used, so in the 1+1d case, we needed 2 different splitting operators. But in this 2+1d case, we actually have 5 different F-move operators, and each set of F-move operators comes with its own phase ambiguity. And so there are basically 5 sets of alpha phases which can be used to redefine the F-move operators. And so the transformation of omega naught is much larger than a coboundary transformation. So the question is, can we use Sahan's trick to define the proper omega, which is actually a cocycle and whose ambiguity is a coboundary? And basically, the answer is that yes, we can, but in this case, we need a ratio of 10 different omega naught terms rather than just the 2. So basically, this ratio has the bare omega naught symbol with arguments g, h, k, and l, and then all of the 9 other elements in this ratio all have at least one identity argument. And so basically this ratio is very carefully engineered so that when these 5 F-move operators are independently multiplied by phase, the ambiguity in omega is precisely a coboundary. In particular, it's d alpha, where alpha is some also a very large ratio of these alpha phases. Point is that defining omega in this way, on the one hand, it can be shown that omega is a cocycle, but on the other hand, it's evidently the case that the ambiguity in omega is precisely a coboundary. And therefore, omega defined in this way gives us an element of the cohomology group.
So just to be sure I understand, I mean, so to argue that this is independent of the position, you sort of imagine moving your honeycomb continuously in space and then arguing that this has to change continuously and implies that. The way you define it is that just specific positions, right? So you define these operators at a specific position.
At different positions, they differ by co-boundaries.
Yeah, so that you can prove very directly.
They could be different at different positions, but they differ by co-boundaries, right?
You're saying if you sort of chose a different mesoscopic lattice to begin with?
A different region, so you are
Oh,
not.
it's different positions on the same lattice even, but okay, for instance.
So this is at site 0. If you compute at site 1,
Yeah, you will find that you get the same homology class, but again, it may differ by. Okay, so so fortunately, as I said, there are sort of 2 methods that I talk about, but thanks to all the good questions, I have only managed to get through the first method that I wanted to talk about. So let me conclude by giving a very basically giving an example of how this method works. So I won't sort of go through the detailed calculation, but I just want to sort of give an idea of how it works in practice. So the example that I have in mind is the boundary theory of a particular Z2 times Z2 SPT in 3+1 dimensions. This SPT is characterized by the topological action A cup A, cup A, cup B, where A and B are both some Z2 H fields. And so basically I will just claim that a microscopic boundary theory of this SPT has the following form. So the Hilbert space is there are two spin halves per plaquette of a honeycomb lattice. And these spins are called sigma and tau. And the Z2 times Z2 symmetry generators have this form. So on the one hand, we just have a simple spin flip of all the sigma degrees of freedom. All
Sigma corresponds to A.
sigma corresponds to A, yes. And secondly, we have this second symmetry generator, which is basically has this form. So first of all, it's a spin flip of all the tau spins, but it's now augmented with this phase factor -1 to the n sigma. N sigma counts the number of domain wall loops of sigma spins. So basically, we say that there's a sigma domain wall on any edge of the lattice, which lies between an up sigma spin and a down sigma spin. So if sigma is up on one plaquette and down on neighboring plaquette, then we say that there's a sigma domain wall lying on that edge. And in the entirety of the system, there will either be an even or odd number of domain wall loops. And so we get this phase factor, which is either plus or minus 1. And so my claim is that these symmetry generators they generate an anomalous Z2 times Z2 symmetry. So let me just very quickly go through the steps of the procedure. The first step is to choose a Hamiltonian which is symmetric and which spontaneously breaks the symmetry completely. So basically, there's a very simple choice of Hamiltonian which meets these requirements. It's just basically an Ising ferromagnet for the sigma spins and for the tau spins. Next, we need to fix domain wall states. Again, we can just basically choose the simplest set of domain wall states which satisfy the requirements that we've laid out. And these states are basically just simultaneous eigenstates of sigma z and tau z operators. Clearly, these are sort of obviously domain wall states of this symmetry breaking Hamiltonian. So far, the form of this symmetry has not entered into the Hamiltonian or the choice of domain wall states. So it had better enter into the third choice that we make, which is to fix the F-move operators. And basically, the F-move operators are defined as follows. We sort of consider sigma plus and tau plus, and then symmetrize these operators to obtain symmetric F-move operators. And so basically, this is the only place that the symmetry comes in is in this symmetrization. Then when we sort of enact the procedure, we find that actually we find that we obtain this omega, but actually the bare omega omega naught actually has the same form as omega. And so in this case, this giant ratio is actually basically all the terms in the ratio drop out except for this first term here. And what we find is that the cocycle we obtain is indeed the one we expect. It indeed describes the SPT phase with this particular action. So this is a very simple example of this procedure in action. So right. I guess I'll stop there because a little bit of time. Yeah.
What's the obstruction in extending this arbitrary dimension?
So the challenge is basically boils down to sort of finding the appropriate ratio for any dimension. And actually, it turns out that there's a recursive formula to there's basically a recursive way to obtain the ratio in any dimension. So we start with the ratio. We start with sort of the lowest dimensional ratio, and then we can build up the sort of higher dimensional ratios recursively. And so this we know how to do. And so in principle, there's not really clear obstruction to generalizing to higher dimensions. But there is sort of subtlety in that it's actually predicted by the cobordism proposal that some of the sort of in cohomology SPTs are actually trivialized in higher dimensions. And so sort of seeing this trivialization explicitly through this procedure is it's not immediately obvious how this would arise. And so basically there's sort of an additional subtlety, which is that in higher dimensions, the domain walls can be sort of decorated by some invertible topological order. And so basically to capture this trivialization, the ambiguity should be larger than just the ambiguity obtained from these phase redefinitions. And so there's some, there is that subtlety which is absent in these low dimensional cases, but sort of rears its head in the higher dimensions. So yeah, but sort of the key workhorse is sort of in finding this very carefully engineered ratio.
I have one more question. So I'm a little bit, F is defined as an inner product, but then your statement is that F is ambiguous up to the sign. How does the sign, like what's happening to the states in the inner product with the sign, with the phase ambiguity? Like F is just an inner product of states F1 and F2, but you're saying that this thing is ambiguous up to a phase change. How does the phase, like what does the phase change correspond to in the states in the inner product?
Basically, each of the two states is shifted by a phase.
That's it? There's no, okay.
That's it.
So I guess the generalization to like one form anomalies in 2+1 dimensions is straightforward, I guess, but what about mixed anomalies between one form symmetries and zero form symmetries? Can you get those by a similar approach?
That's a good question. Is it obvious too that the general relations in one form is already?
That's not just the lift everything one dimension. No, okay, of course, there may be subtleties there.
I'm not even sure about the one form case. So I've thought a little bit about the one form case, and basically it feels like what should happen. Basically, the analogous procedure in the one form case, I think should basically correspond to this sort of T-junction process, which is sort of originally used by Kitaev to define the topological spin of an anion. And as far as a mixed anomaly between zero form and one form, I guess that should correspond to some symmetry fractionalization of the zero form one, like the anion that generates the one form. But I don't know. Yes, so far I don't know exactly how to generalize this precise procedure to the higher form case. It's something I would be interested in.
Will there be more consistent conditions because now you have all dimensions, not only two dimensional surfaces?
One subtlety is that in one form symmetry, they are not characterized by good cocycle, they are by spin of the anion. So the question is how you translate the spin to some cocycle because it's H. It seems that there is some question which in the Zoom. Can you unmute?
Yes, thanks for the talk. I have some question about the setup of choosing basis of domain wall states. Do you require to have a complete basis? In which case, it seems like you need to have a macroscopic choice of sites from 1 to n. But you mentioned it seems like you're suggesting that you don't need all sites on which you can apply the symmetry.
The domainal states definitely don't form a basis. I mean, the set of domainal states is much smaller than the set of, some set of basis states. In fact, I don't even think it's necessary that distinct domainal states are orthogonal. But they certainly don't form a basis because there's just far too few of them.
So how does your choice of xi, say for the 1+1d case, how does your choice of sites xi on which you allow domain wall to appear affect your anomaly detection?
So basically, distinct choices of domainal states, which could also differ by the choice of location of domain walls themselves, will always change the cocycle that we obtain by some coboundary. But of course, changing by a coboundary does not affect the actual cohomology class. So regardless of which domainal states we choose, we always get the same cohomology class.
Thank you. Thank you very much.
Let me ask one question. So in the 1+1d case, you take a ratio of 2 of these guys, and the thing in the denominator, if you actually impose translation symmetry, it becomes a mixed anomaly between translation and your internal symmetry. So in this case, the extra stuff that you're modding out, well, can you interpret them as the mixed anomaly between this internal symmetry and translation or lattice rotation?
I don't know, but it'd be very interesting if that were possible. But at the time being, I don't know if it has such an interpretation. It'd be quite interesting to look at.
Any other questions? If not, let's thanks Wilbur again.